Welcome back to Daniel's Extra Chemistry Help classes. In the last class we discussed significant figures and measurements and calculations. Also dimension analysis for problem solving. Today we will be just discussing laws of chemical combinations, Dalton's atomic theory, atomic mass and atomic mass unit, atomic mass from isotopic masses and percent abundance, and also molecular mass determinations. Okay, let's go to the first one topic, which is the laws of chemical combinations. Okay, now I have to say two things about these laws. These laws are the result of scientific experimental research done by pioneers in chemistry like Lavoisier, Dalton, Avogadro, etc. Okay, second one is these laws led John Dalton to propose the first scientific atomic theory known as the Dalton's atomic theory. Okay, now for those interested in history of chemistry, these searches done by these scientists were done in the latter part of 18th and the first part of 19th centuries. Okay, let's go look at the laws of chemical combinations. The first law is called law of mass conservation. Now, Lavoisier was the chemist who has done a lot of preliminary work on this one, and while he was doing chemical experiments, he found that the total mass of the reactants is always equal to the total mass of the products. So his law, which is called as the law of mass conservation, is now, most of the students know that actually. It's called in a chemical reaction, matter is neither created nor destroyed. And that is very famous now. Okay, the next law is called law of definite proportions. Okay, now we are considering a single compound for this particular law. Now, usually I ask students, what is the one compound very essential for life? That means if you're going to Mars for an expedition, if you want to live or if you're looking for life in the Mars, what is the one compound you will be just just trying to find out? And most of the students will say it is water. Okay, so if you take water, the water contains hydrogen and oxygen, two elements, and the mass ratio of the hydrogen and oxygen is 2:16, or say 1:8. Now, when I usually discuss this, numbers, students usually ask, where do you get all these numbers from? Okay, all these things are present in the periodic law. I mean, periodic, the tables. So, periodic table is a very important resource for chemists, and for every, element we have an atomic mass. So here, the atomic mass of hydrogen is 1. Since there are 2 hydrogens, I have taken 2. And 1 oxygen, atomic mass is 16. So the 2:16, that ratio comes from, just the periodic table. Okay, now, this applies to all compounds. Any compound, if you take any sample, if you take different samples from different sources and analyze, you find that the mass ratio of the elements in the compound is fixed. It doesn't change. That is what we call as the law of definite proportion, and the law says that the same compound always contains the same elements combined in the same mass ratio. Okay, now if you take water, we already seen the ratio is 1:8. And what is the application? Now, since there is a definite composition or a fixed composition, you can find the mass of elements in a compound by using that mass ratio. For example, if you take 500 grams of water, that is, one bottle of water, you can find out how much hydrogen is inside that water by taking the ratio. Out of the 18, 2 plus 16 is 18. Out of the 18, 2 is hydrogen. So 2/18 is the ratio for hydrogen in the water times 500 grams is going to give you 55.6 grams. So that's going to be your mass of hydrogen in that particular compound. So it's a very important and useful idea. We can actually find mass of elements. If you want to find the mass of sodium in sodium chloride, that's our table salt, you can find it out by using this method. Okay, now the third law is called law of multiple proportions. As the name indicates, we are looking for more than one compound. For example, let us take a typical example. Carbon can combine with oxygen. Usually if carbon is burning in oxygen, enough oxygen or in more oxygen, we are getting carbon dioxide, which is a it's not a poisonous gas, which is usually formed in all combustion reactions. Okay, but if the quantity of oxygen is less, this can happen in many ways. If a car runs in a closed garage for a long time, the oxygen content inside the garage may become less and you may get this type of a reaction. You have to be careful. Why? Because when carbon combines with oxygen, with one carbon and one oxygen, you get carbon monoxide. That is another compound, but that is a toxic gas, very poisonous. Okay, so let's come to the law again. So carbon can combine with oxygen, giving two oxides. One is carbon dioxide, other is carbon monoxide. And you can take the ratio, 12:16 for carbon monoxide, because one carbon and one oxygen. And you can take 12:32 for carbon dioxide, which is one carbon and two oxygens. Already we discussed how you got the numbers. Okay, the law says, if two elements combine together giving more than one compound, then the masses of one of the elements which combine with a fixed mass of the other element, is in a particular ratio or in a fixed ratio. That's actually said. There are different versions of this law. Here I have two elements combined to form more than one compound. The masses of one element that combine with a fixed mass of the other element are in the ratio of whole numbers. So you get whole number ratios. So in this case, see carbon, if you take, we got fixed mass, see that 12 and 12. So what is the different mass? 16 and 32. So we have to take what? Take the ratio of the 16 and 32. That's what we have. So ratio of masses of oxygen combining with the 12 grams of carbon is going to be 16 in the first compound and 32 in the second compound. If you take the ratio, it's a very simple ratio, 1:2. So this is the whole thing about multiple proportions. Okay, now let's think about a problem, combining the definite proportion, multiple proportion, that idea. Okay, question is this. Check the given data, there is there on the right hand side, of nitrogen reacting with oxygen, giving nitrogen oxides of nitrogen. Okay, and that particular data support the law of definite proportion or multiple proportion. Okay, what is the idea? We already know that definite means we only have one compound. So one fixed ratio should be there coming out of the first experiment and second experiment. That means the mass ratio should be the same. But if they are different, then you have to check what? You have to check the law of multiple proportion. So what is the idea? Mass ratio should be the same for definite proportions. If we take the mass ratio of oxygen to nitrogen, in both cases, it should be the same for a definite proportion. But if it is not fixed or the same, then you have to check the ratio of the different masses. That means the mass of oxygen combining with 1 gram of nitrogen in both cases. And what you should get? You should get a definite simple ratio. So let's take this particular calculation. So I'm taking oxygen mass to the nitrogen mass and oxygen mass. So oxygen to nitrogen mass I'm taking. So oxygen divided by nitrogen mass. First case you get 1.14. In second case, I again doing the same type of ratio, I'm getting 2.28. So definitely this means what? You're not having the same ratio or same mass ratio. So it's not definite proportions. Then you have to check what? Check the different masses which we are getting here and find out whether you are getting a simple ratio. So what you are going to do? You're going to take the 1.14 in the first case and 2.28 in the second case. So you take that. So since the mass ratios are different, this is not a case of definite proportions. But the ratio of different masses of oxygen combining with the 1 gram of nitrogen, in this case what you are getting is combining with 1 gram of nitrogen. And you're getting what? A simple ratio. So definitely it's the law of multiple proportions. Okay, now let's go to the third law, which is called Gay-Lussac's law of gaseous volumes. Now Gay-Lussac has done a lot of experiments with reactions in between gases, and the law says that when gases combine together giving gaseous products, there is a simple ratio between the volumes of the gases at the same temperature and pressure. And there are different versions. This version says that when gases combine or are produced in a chemical reaction, they do so in a simple ratio by volume. So you are taking the ratio of the volumes at the same temperature and pressure. For example, let us take a typical example. If you just consider the hydrogen gas and chlorine gas combined giving hydrogen chloride gas, chemical reactions is shown to have 50 milliliter of hydrogen and 50 milliliter of chlorine giving 100 milliliter of hydrogen chloride at the same conditions of temperature and pressure. Now you take the volume ratios, it is 50:100, and what is the ratio, simple ratio? 1:1:2, which is a simple ratio. This is what is Gay-Lussac's law of gaseous volumes. Okay. Now let's go one of the most important law in this set, which is Avogadro's law. It looks very simple, but it has got a lot of application. That's why it's so important. Now here what are we doing is, you're taking equal volumes of gases. That means you can take any gas. It may be an elemental gas like helium, which is a monoatomic gas. Monoatomic means each molecule contains only one atom. Or ammonia gas, which is a compound gas. Okay, the last one is oxygen, which is a diatomic gas. Each molecule contains 2 atoms of oxygen. So whatever be the type of gas you have, if you're taking equal volumes of gases, what is the law saying? Equal volumes of all gases at the same temperature and pressure. That means the conditions of the temperature and pressure should be the same. They contain equal number of molecules. And this is a very famous thing, and also it's so famous that you can actually remember it by just remembering that equal volumes contain equal number of molecules. The other things comes with that. So just keep that in your mind. Equal volumes contain equal molecules. Now what is the applications of this? One or two applications I can say here. Look at that. From the law it is derived that elementary gases are diatomic. So what do you mean by elementary gases? So gases which are actually elements. For example, hydrogen, nitrogen, oxygen, fluorine, chlorine, all these are diatomic. So when you write these gases in your chemical equations, we always write them as H2N2O2F2. Now students are usually worried, how will you know that which are the elementary gases? Now this comes into periodic table at the first, if you look at that, it's at the top of the periodic table. You can know by that. Or you have mnemonics. If you are just interested in a mnemonic, I can say, horses need oats for clear brown eyes. Okay, what's that? Hydrogen horses need is nitrogen, oats is oxygen, 4 is fluorine, clear, that is Cl, brown eyes are bromine and iodine. See, iodine is actually your eye, it's just an eye. Okay, that's the first one. All of them are actually diatomic, which is actually proved from the Avogadro's law. Molar volumes of all gases under the same conditions of temperature and pressure are the same. Is another application of Avogadro's law. What do you mean by molar volume? volume of 1 mole. Now we already know from the, when we studied about units, the SI unit for the quantity of a substance is a mole. So we'll be studying more about the mole, when you're actually going a little more in this same chapter. So molar volumes means volume of 1 mole of any gas. Molar volumes of all gases under the same conditions and of temperature and pressure are the same. So whatever we just discussed, the helium, the ammonia and oxygen, if you take the molar volumes, you are actually taking 4 grams of helium, 15 grams of ammonia, 32 grams of oxygen. You will eventually know how to take the number, the masses. They are having 1 mole in each of them. And all these gases, see, the masses are entirely different. See, 4 and 15. So actually, almost 4 times, ammonia mass is 4 times. And, 4 and 32, see, is 8 times. But even then, the volumes are the same. That's a pretty interesting idea. And also, one other thing you can always remember and is helpful to you is the molar volume is equal to 22.4 liters under standard temperature and pressure. Usually we call the standard temperature and pressure as STP. So if you take the gases under standard conditions of temperature and pressure, standard temperature is 0 degrees Celsius and standard pressure is 1 atmospheric pressure, the volume of 1 mole of any gas is 22.4 liters. Keep this number in your mind, because this may be useful to you when you come to do problems. So these two are very, very important applications coming out of the Avogadro's law. Okay, so we already discussed all these, laws of chemical combinations. What are they actually leading to? Actually, from these laws, Dalton found out, or he actually proposed his theory of Dalton's atomic theory. Okay, so we already know that the ultimate particle is what we call as actually, or the indivisible ultimate particle is called as the atom. Now, even centuries before Christ, Indian and Greek philosophers have been, speculating about an ultimate particle. They have got their own way of looking at ultimate particle. And the Greek philosophers call the ultimate particle as atomia. That was their idea about the ultimate particle. If you just go on dividing, a solid substance or any substance, ultimately you'll come to a last particle which you cannot divide. That is their idea. But Dalton's theory is a little different, because this is based upon what? The experimental determinations or experimental theories or experimental laws. We already discussed this. That's why this is very important. So the first scientific theory of the atom, which is the ultimate particle which you are talking about, comes from Dalton's atomic theory. Now from this, what actually Dalton found out was that the theory of Dalton is this. The first one, matter consists of indivisible atoms. That's the first postulate of the atomic theory, Dalton's atomic theory. Second postulate is atoms of a given element, that means a particular element, are identical in all respects. Like, the mass or properties, they are all identical. And atoms of different elements differ. The third idea is compounds are formed by, when atoms of different elements combine in a fixed ratio. So a definite number of atoms of different elements combine together, giving compounds. Finally, in chemical reactions, there is only rearrangement of atoms. No atom is created, no atom is destroyed in a chemical reaction. So these are very, very important, and you can say the principles which are behind even now we have these ideas for an atom. So this is a starting point of the atomic theory. Okay, now when you think about the masses of atoms, how to express the mass of an atom? We call it atomic mass. Remember, atoms are very, very, very small. You have millions of atoms at the tip of a pin. So how will you express the mass of an atom by using usual units? It's very difficult. So what are the scientists thinking about? They thought that you cannot express the mass of an atom by usual units. So you have to find out another unit. So the history behind the atomic masses is they started using the lightest atom, which is the hydrogen atom, as a standard, and one atom of hydrogen was taken as the standard. So by using that, what is the plus point? Every atom has atomic masses more than one. That was their idea. But the problem with hydrogen is hydrogen cannot combine with many elements. So practically it's very difficult to just do compare the masses of atoms together. So scientists thought oxygen will be a better idea. Oxygen combines with many other elements. But the oxygen on the hydrogen scale has an atomic mass of 16. So if you want to keep the mass of hydrogen as 1, you have to take the unit as 1/16th of the mass of an oxygen atom. So that was the second unit which scientists considered. But eventually scientists found that every element has 2 or more isotopes. What do you mean by isotopes? They are atoms of the same element with different masses. Now, this is something different from your Dalton's atomic theory. Dalton didn't know about, isotopes at that time. But now we know that elements have 2 or more, types of atoms in naturally. So scientists thought that instead of taking, different masses, you have to take only one mass. That means you have to take only one isotope. And the convenient isotope they took was carbon. And carbon on the hydrogen scale is atomic mass 12. So 1/12 the mass of carbon 12 atom is taken as a unit. So the definition of the atomic mass is the number of times an atom of an element is heavier than 1/12 the mass of a carbon 12 atom. So carbon 12 is the present standard for finding atomic masses. Okay, now, so that unit which we have said, that is 1/12 the mass of a carbon 12 atom, is called the atomic mass unit, or it's also called the unified atomic mass, unit, which is U. And in the usual grams, the mass of, the atomic mass unit equivalent is 1.66 times 10 to the power of -24 grams. So small a number. Okay, so atomic mass is the average mass of the isotopes of the elements as they occur in a natural sample. So I already told you, natural sample of elements always have 2 or more isotopes in different ratios. So you take a natural sample and find the weighted average. That means you have to take into consideration how much ratio of that particular isotope is there, and that weighted average gives you the atomic mass. Now how can we do this? This can be easily done by using an instrument which is called as a mass spectrometer. You take a sample of the pure sample of the element, inject it into the mass spectrometer. Mass spectrometer is going to what? Separate the different isotopes. And it will give you how much percentage of a particular isotope is there, as well as it will exactly give you an accurate, record of the atomic mass, the mass of the isotope. So the mass of each isotope is known, and also the percentage, which we usually call as the percentage abundance. So the two things which we know from the mass spectrometer is the mass of each isotope, accurate mass, and also the percentage of abundance. So if we know these two things together, we can easily calculate the average, the weighted average of that particular element. For example, if you take carbon, carbon has mainly two isotopes, carbon 12 and carbon 13, and it traces of, sometimes you also get carbon 14. Small amounts of carbon 14 is also there. But if you take chlorine, and if you analyze chlorine, we see that there are only two isotopes, mainly two isotopes. One is chlorine 35, the other is chlorine 37, and the natural abundance is 75.77 for the chlorine 35, and its molar mass is from the spectrometer is 34.9689. The second isotope, chlorine 37, has a natural abundance of 24.23%, and the molar mass is 36.9659. So if we know these two values for all the isotopes of that particular element from the spectrometer, we can easily calculate the your average atomic mass. So convert the percentage of abundance into fractions. So percentage into fraction means what? Percentage is out of 100. So divide the percentage with 100 to give you the fraction. Multiply each isotopic molar mass with the fraction. So each, they change this into fraction, multiply with the molar mass, change this into fraction, multiply with the molar mass. Do that for all the isotopes, then add them together. That will give you the weighted average which we are looking for. For example, for this one, the 75.77 become 0.7577 by dividing with the 100. Multiply that with 34.9689 plus 2423 will change into 0.2423 times 36.9659. Add them together, you get 35.45 atomic mass unit. That is the average atomic mass of this particular element. This can be done for all elements. It's actually done for all elements, and whatever you get on the periodic table are average average atomic masses. Okay, now there's one problem. What will be the mass of one carbon 12 atom? We're talking about one atom in grams. That means usual value. Now there are different ways of doing this, but the easiest way is what? We know carbon 12 is actually our standard, and the isotopic mass of this one is 12 AMU, which is coming from our definition of the atomic mass unit. Okay, now the superscript of the atomic mass symbol here is the mass in AMU. Use the conversion factor. We know that one atomic mass unit is 1.66 times 10 to the power negative 24. We already defined that, and we already know that. So just use that equality and convert that into what? A conversion factor. So the AMU and AMU should cancel out. Your gram should be on the top. So just multiply the 12 AMU with 1.66 10 to the power negative 24, and the value is 1.99 10 to the power negative 20. You can do it for any atomic mass. You can convert it into grams by using this idea. Okay, what's the definition of a molecular mass? You can define a molecular mass just like we have defined an atomic mass, but practically if you want to find the molecular mass, you just what? Add up all the atomic masses in the molecule. It's a typical example of a molecule. We have got carbon atoms. The dark atoms are carbon, the lighter atoms are hydrogen, and the red ones are the oxygen. So it's actually propylene glycol. So if you just add up all the atomic masses, so molecular mass is the sum of the atomic masses of the elements present in a molecule. So what do you do? Multiply each atomic mass by the number of atoms in that particular molecule, then add. For example, water is a typical example. 2 hydrogen atom, 1 oxygen atom. In the periodic table, if you see the correct atomic mass is 1.008, usually we take approximately 1. That will be easier for us. So 2 times 1.008 plus 1 times 16, which 16 is the atomic mass of oxygen. Add them together, you get 18.0 atomic mass unit, which is the molecular mass of water molecule. But the propylene glycol, the molecule we have here, we got 3 carbon atoms. If you look at that, you get 3 carbon atoms, 8 hydrogen atoms. See the lighter atoms, which are, 8 hydrogen atoms, and the red ones are the oxygen atoms, 2 oxygen atoms. So multiply 3 with 12, which is the atomic mass of carbon. 8, which is the hydrogen atom, times 1, which is atomic mass, approximate atomic mass. And then, 2 times 16, which is atomic mass of, oxygen. Just add them together, you get 76 AMU, atomic mass unit, which is the molecular mass of, propylene glycol. So, usually, you have to do the molecular mass many times because many calculations need the molecular mass, you calculate it. It looks pretty simple, but many times what happens is students usually do, incorrect, molecular masses. So we will be very careful about it, that the number of atoms you are taking and also the atomic mass from the periodic table. For example, the ordinary sugar we use, the table sugar we are using is a C12H22O11. So what do you do? 12 times atomic mass of carbon, which is 12, 22 times the atomic mass of hydrogen, which is 1, 11 times the atomic mass of oxygen, 16, then what? Multiply and add them together, you get 342 atomic mass unit. Okay, let's go to the next one, aluminum sulfate. Now in this case, there are 2 aluminum atoms. Then the sulfate radical, which is SO4, is multiplied with a 3. So the 3 multiplication applies for sulfur as well as oxygen. So basically you have 3 sulfur and 12 oxygen atoms. You have to be careful about that. This is where students actually usually are, so what we can do, is just go by the formula. So 2 aluminum, 2 times 27. 27 is atomic mass of aluminum. Then put a parenthesis. 1 sulfur, so 1 times 32. 4 oxygen, so 4 times 16. And then close the parenthesis and multiply with a 3. Don't forget that. So I'm just going just like the formula. So that I have no problem in, there's no error in the calculation. So if you do this on your calculator, you're going to get what? 342 atomic mass unit. So do this, you have to be careful about that. Next one is chloroform. Pretty easy. 1 carbon, 1 hydrogen, 3 chlorine. So this what? 1 times 12, 1 times 1, that is the hydrogen. And then 3 times 35.5, which is the chlorine. Add them together, you get 119.5 AMU. Okay, now the other compound is sodium carbonate decahydrate. It's actually a salt with water crystallization. So when you have this type of thing, you have to be careful. When you say 10H2O, there are 20 hydrogen atoms and 10 oxygen atoms. Don't forget that. So you have to be careful. So what's the idea? Just go with 2 times 23, which is sodium, 1 times 12, which is carbon, 3 times 16, which is going to be oxygen, and I'm going to use 10 times in parenthesis. I'm going to take the water in the parenthesis. 2 times 1, 1 times 16, and if you do correctly on your calculator, put the parenthesis in the calculator. You can do that, and it gives you 286 atomic mass unit. So be very careful that you have no problem with finding, molecular masses. Okay, now let's come to a problem here. Look at this problem. It's a pretty interesting problem. Carbon has 2 naturally occurring isotopes. I already told you the third one, the carbon 14, is actually in only traces, so you're not taking that. So carbon occurs in 2 naturally occurring isotopes. Carbon 12 abundance is 98.93%, and the isotopic mass is 12.0. So because that's the definition thing. And carbon 13 abundance is 1.07%. The mass, isotopic mass, is 13.0034 AMU. Okay, without doing any calculations, you should not do any calculations. Determine which mass is closest to the atomic mass of the carbon. So out of the 3, which is the best choice? Is the question asked. Okay, now if you look at that, you know that if you take the percentages, 98.9, that means almost 99% of the mass average comes from the atomic mass 12. The other one is only 1%. So, can it be 13? No, never. Because it's not near to the 13 at all. Can be 12.50? That means you have 50-50. That means 50% of the 12 and 15%, 50, that is not the case. So we can easily say this is the correct answer, because your atomic mass is going to be, the average is going to be nearer to the 12. So this is an idea which you can easily use. Since the natural sample contains almost 99% of carbon-12 isotope, the isotope atomic mass would be very close to 12.00 AMU. So the choice is A. Okay. So just think about the discussion we had. If you like, please respond and subscribe, and send your suggestions, questions, even thumbs up, so that I can be helpful to you, and I can, you can also get your, lessons. Whenever I just put the lessons, new lessons, you can easily know when it's actually coming out if you subscribe. So please do that. Thank you.